Okay, so hello everyone and welcome to the week 5 of tutorials for introduction to automata languages and computation. So last week we looked at what are called as regular expressions and okay. Okay, so last time we saw what is called regular expressions and yeah, and we saw that if I give you a regular expression, then there is an equivalent epsilon NFA for the same, and hence there's an equivalent NFA as well as a DFA. So the other side of the equivalence is something we will be looking into this week. So this week we will see that if I give you a DFA, then there is a way to convert it into an equivalent regular expression. So we will look into some examples of this kind. So that will basically put our regular expressions into this class of models that capture regular languages. So these are our regular languages. And we saw different models that that accept the regular languages. So for example, we saw DFAs, then we saw these are equal to NFAs, then these are in turn equal to epsilon NFAs, and now we will be putting regular expressions into this category. So so that's basically the agenda. We will look into some examples of this kind. Then we will also be looking at properties of regular expression. So basically, if I give you two regular languages, then what if like you apply different operations on them? Then is the resultant language regular or not? We'll be looking into such examples. Also, in week 3, there was some example that we were looking, some DFA construction that we were looking into, and someone pointed out that the recording somehow got cut before we completed the example. So at the end of this tutorial, we will finish up that example as well. So okay, so let's start with let's start with problems. Okay, so I think I'll take this example towards the end because this will be involve a lot of calculations. So we'll do it towards the end. So okay, so let's start with properties of regular expressions. So yeah, so let's say you have been given two regular languages. So A is a regular language which consists of all words that starts with, let's say, 0, and B is the language which consists of all W that end with 10. So for example, A would consist of words such as 0, 0, 1. Also, like throughout the examples, if we don't mention anything, then the alphabet is implicitly considered to be 0, 1. So A looks something like this: 0, 0, 1, 0, 0, and so on. And so on. And B looks something like this: 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, and so on. So I think, yeah, you get the idea. So this is these are regular languages because you can draw a DFA for the same. And we have done like plenty of examples like this in the previous weeks. So what we're going to do is you're asked whether the following, if you apply following operations such as union, intersection, and we'll discuss what are the other two operators. So if we apply such operations, and what happens to the resultant language? Is that language necessarily regular is the question. So I'll wait for a couple of minutes if you have answers, and we will discuss the solution then. Okay. So yeah, let's look at. Okay. Okay. Good. So yeah, let's see. Whether the answer is correct. Okay. Uh, so let's try A union B. But before that, maybe as a warm up, let's just draw the DFAs for languages A and B. So what does A look? What does the DFA for A look like? You maybe, let's say you start at a state A. If you see a zero, yeah, then you accept everything after that. But if you see a one, then you go to a reject state, let's say C, and thereafter you just loop into that state. So what this automata captures is captures all the language consisting of all the words that start with zero. So this is your this is your machine corresponding to the language A. Now let's draw the machine B. What does B look like? So if you see a one, let's say you go to Q, then if you see a zero, you go to the final state. But you want to make sure that this is the final string that you read. So if you see zeros before this, you basically stay in the same state. At Q, if you see a one further, then you stay at Q. And at R, okay. And at R, if you see a zero, then basically it's as good as like you have say read something 0010. Okay, and now at you are at R. Now if you see a 1, then basically you are waiting for a final 0 to come. So what is the state that captures that? That is Q, because Q kind of tells you that you have read 1 and now you are waiting to see a 0. So if you are at R and you see a 1, then you should go to Q. And if you are at R, let's say, and you see a 0, then it's as good as you are freshly looking for a new batch of 10, because you don't have you haven't read 1 in the last state. So you should go to P. So this goes to P on 0. Yeah, so that's the machines corresponding to A and B. Now uh, let's try to draw for the strings that start with okay, maybe I'll do B first, which is A intersection B is the set of all W such that W starts with A with 0 and ends with 10. So yeah, so what does A intersection B look like? So it consists of strings like this. It may have 0 1 0, then it may have read like bunch of ones before it sees a 0, or 0 1 0 1 0, and so on. So it just makes sure that you have read a 0 at the start and 10 at the end. That's it. So let's try to draw an automaton for the same. So what you do is you, let's say, start at A. Then if you see a 0, you should go to a new state. Then and if you see a 1, then you should stop the, I mean, sort of go to a dead state and reject everything, because your string has to start with a 0. So now if you are at B, then you have seen a 0. Now there could be a lot of strings that come in between, but at the end we want to read a 10. So yeah, so at the end, if you have read a 10, then we want to accept. But there may be strings that occur in between, so we want to manage them by drawing arrows to the appropriate states. So if you are at B and you see a 0, then you stay at B. If you are at C and you see a 1, then it's as good as you are I mean, you have read something like 0 1 and now you see a 1, then you are waiting for a 0. So C is basically the state that captures this. So you should stay at C if you see a 1. And at D, if you are at D and you see if you see a 0, then basically it's as good as starting from B, and if you are at if you see a 1, then it's as good as starting from C. So yeah, so this is the automaton that corresponds to A intersection B, because it will only accept those strings that start with 0 and end with 10. So maybe if you want to take a test case example, let's say you have this string 0110. So let's see how the computation proceeds. So you are at A in the beginning, then you see a 0, you go to B. Then you see a 1, you go to C. Then you see a bunch of 1s and you continue to loop on C. Then you see the final 0, you go to D. So I hope you are pretty much convinced that this is indeed the automaton corresponding to A intersection B. So while we can sort of intuitively come up with automata like this by looking at the language and adding states and transitions as and when we need, depending on what language we want to accept. But it could be that the languages A and B are very are very complex, or there could be complex operations that you are doing on the automata. So there is a there's a like step-by-step procedure to always obtain a DFA for the intersection of regular languages. So we will look at that procedure. So the advantage of the procedure is that even if you have very complex languages, you don't really have to think what transition to put and so on. You just follow this procedure and you are guaranteed to end up with an automaton corresponding to intersection B. So we will. There are also other advantages of the procedure that we will look into once we discuss the solution. So what I'll do is I'll try to get this page duplicated. Okay. Okay. So what we will do now is what is called a product construction. So what does product construction do? It gives you a step-by-step procedure to obtain the machines corresponding to uh, intersection of two regular languages or union of two regular languages and so on. You can see you can do much more with the procedure. It's much more general. But for now, let's since we're looking at the intersection example, let's design for the intersection example. So what does this product construction intuitively do is you are kind of capturing two conditions here. So if I give you a string 1100 or something, what you do is you run the string on the machine MA, then you independently run next on MB. Now you are going to accept only when both of them accept, because that is the intersection condition. It says if the string is in both A and B, only then you accept. So that means if both accept X, then accept. Otherwise, you're going to reject. That follows naturally from the definition. So what the product construction is going to do is it's going to intuitively translate this in terms of a DFA. So what we do is at every state you're going to remember, if I read say 0, then where do I go in the machine MA and where do I go in machine MP? So you're sort of remembering both things in one state. That's so yeah, so let's see how to do that. Okay, so you have three states on the machine in MA and you have three states in MB. So what you will get is you will get 9 states altogether. So your states look like this. You have AP, you have AQ, then you have AR, then you have BP, BQ, and BR. Then CP, CQ, and CR. So what we have done is we have taken one state of the machine MA and taken basically all possible combinations of the set AB and PQ. So this is nothing but Q is nothing but ABC cross PQR. So we are just looking at all possible pairs that can happen. Okay, so yeah, so in the machine MA the start state is A, and in machine MB the start state is P. So in the new machine the start state should be AP uh, because A is the start state in MA and P is the start state in MB. So now you start at at AP, and if you see a zero, then yeah, if you see a zero, then what happens is you are at AP and you see a zero. So uh, in MB, if you see a zero, then you go to state B, and in P, if you see a zero, you stay at P, because that is what the transition is defined. From A, you go to B, and from B, if you see a zero, you stay at P. So from AP, what is the transition that is defined? From A, you get to B, so you write a B here. From P, you stay at P, so you write a P here. So that will give you the new state that you will reach on seeing a zero. So similarly, can you maybe try and tell me where should the transition go if you see a one? Okay. So if you are at if you are at A and you see a 1, you go to C, and if you are at P and you see a 1, you go to Q. So CQ is the corresponding transition. So let me draw an arrow like this. Now, yeah, now let's try the same. Sorry, really sorry. Yeah. So now let's try the same for AQ. If you are at AQ and you see a 0, then A takes you to B and Q takes you to R. So from AQ, you draw a transition like this. Okay, sorry. I think this should have been BQ. Yeah. Yeah. And if you are at AQ and you see a 1, then A takes you to B and Q takes you to Q. So you have a transition like this here. So let me quickly complete all of this. You can also try to complete this on your own. Okay. So okay. So okay, so let's look at what should be. Okay, so what I've done is, let me quickly tell you. So what I've done is from AP, you reach these two states, BQ and CQ. Then I tried to, we did, I mean, so then we basically started drawing transitions for the new states that we are reaching. Now, what should be you can also try to complete all the transitions for the entire thing, but it's sufficient to do it for those states that are reachable. So, okay, maybe I think we did not do CQ, so let us try to finish that up. So CQ is basically C stays at C, Q goes to R. So this goes to R, and on 1 it stays here. Then you have CR. CR on 0 goes to CP, and on 1 it goes to CQ. So yeah, you have CP on 0 and CQ on 1. Okay, so okay, maybe I'll just anyway complete everything. So you are at CP and you see a 0, then C stays at C, P stays at P. So this is a self loop on CP. If you see a 1, P goes to Q, so CP goes to CQ. Yeah, so okay, I think now we are, yeah, we have completed all the transitions, and it's fine if some of the states are not even reachable. Okay, so now what we're going to do, so what we've done is it tells you that, okay, if you, yeah, okay, if you were at, let's say, state A and you see a 1, then you would have gone to C. So the first letter of this tuple would be C. And if you were at P and you see a 1, you would have gone to Q. So hence you have the CQ. So we've done this thing for all the reachable states. Now the thing that we want to identify is what should be the final states for this automaton. So let's see, when do we want to accept? So we said that we want to accept when both machines A and B, both of them accept. So machine A accepts if and only if you reach the state B, and machine B accepts if and only if you reach the state R. So what you want to do is you want to reach both the states B and R. So your final state should be BR. So what we'll do is we'll make this a final state because both B and R are the final states in it. So now your automaton corresponding to A intersection B looks like this. But you can basically remove all the states that are not reachable, and it would, like, we can simplify this by removing the states that don't even play a role. So just to demonstrate, let me draw this thing again with a simplification. So you are at EP, then if you see a 0, you went to PQ. So on 0, you went to BQ. I'm just drawing the same thing but with by removing some of the states. If you see a 1, you went to CQ. Then from BQ, if you saw a 0, you went to BR. If you saw a 1, you stayed there. Then from BR, okay, BR is the final state. From BR, if you see a 1, you go back to BQ. And if you see a 0, you go to BP. And what does BP do? On 0 it stays there, on 1 it goes to BQ, CQ goes to CR, CR goes to CQ on 1, then you have CP, which yeah, so CQ goes to CP and CR goes to CP on 0. So this is the automaton that you get. And let's look at what are the strings that are accepted. It will only accept when you definitely start with 0. If you started with 1, then you never ever reach a final state. So all those strings that start with 1 would be rejected. Now if you start with 0, you go to BQ. Then okay, I think, yeah, then you stay here until you see a bunch of 1s, and if you see a 0 later, you end up accepting. So yeah, so what I want to what I want to demonstrate now is that the advantage of doing this product construction is that you can solve uh, like union or other operations as well using the same idea. So let's say if I were to modify this in order to accept A union B, Then maybe I'll take a fresh page. Okay, so if I have to accept A union B, then when do we want to accept? We want to accept if MA accepts a string X, or if MB accepts X. So when does MA accept? MA accepts when it is able to reach its final state B. So if MA reaches, or let's say X reaches B, or if X reaches the final state of MB, which is R. So basically, it doesn't matter what state in MB we have reached, as long as you have reached B in A. So that means your set of final states would be PB, PQ, PB, QB, and RB, because all of them have. Okay, I think we defined it the other way around. So you have BP, BQ, and BR, because all of them have final state of B. Similarly, symmetrically, if you think about it from the other conditions point side, then you would accept if X reaches R, and it doesn't matter what machine A is, what is the state of machine B. So it could be A, B, or C. So you can have AR, you can have BR, which is already written here, so I'm not repeating the element, and you can have CR. So if you reach any of the states, then you would basically you would accept it for A union B. In case of A intersection B, you wanted the yeah. So this basically is the set of all PQ such that P is an accept state in MA, and Q is an accept state in MB. And the only thing we changed here is, for the case of union, you change this condition to OR, and hence you end up getting so many states. So what this tells you is that if I give you any regular languages, any set A and B, you can always do this product construction by modifying the transitions and final states and start states, and you would end up with a regular with a DFA for A union B and A intersection B. Now let's look at C and D. So C says what happens to A parity B. So let's define what is this A parity B. So this is set of all strings W such that W is in A but not in B, or W is in B but not in A. So what that means in terms of our languages, because A is the set of all strings that start with 0 and B is the set of all strings that end in 10. So for us, that would mean that W is set of all strings such that W starts with 0 but does not end in 10, or sorry, yeah, or W starts with, sorry, does not start with 0 but ends in 0. So this is the language that we have. Now, while you can like directly go and draw a DFA for this, the advantage of the method that we just saw is that you can directly draw a product construction for the same. So what you will do is, because basically this language is nothing but, if you think of this in terms of Venn diagrams, if this is A and this is B, then A parity B is basically this shaded region, this union this. So what is this in terms of sets? This is A union B set minus A intersection B, because A union B is basically this entire region, and A intersection B is this region which is subtracted from the entire region. So you would get A parity B, which is nothing but A union B set minus A intersection B. So now if you think of L1 as A union B and L2 as A intersection B, then we know that L1 and L2 are regular, because that's what we did in part A and B. We said that if two languages are regular, then their intersection and union is also regular. So basically this means this is nothing but L1 minus L2. And we know that this is nothing but L1 intersection L2 complement. Is that fine? So yeah. So now we know that L1 is regular. We know L2 is regular. So if we can show that L2 complement is also regular, then by again repeatedly applying the property of closure under intersection, you would get that A parity B is also regular. So notice that we saw this in previous tutorials, that if L is regular, then L complement is also regular. So how do we show that? The idea is very simple. If you have a DFA for L, what you do is you simply take all the final states of the DFA, make it non-final, and take the non-final states and make them final. So basically you are swapping the final and non-final states. So if you do that, then what happens is everything that was accepted earlier gets rejected now, and everything that was rejected earlier gets accepted now. So this is a easy sort of intuitive way to show that if L is regular, then so is L complement. So in this case, L2 is regular, hence L2 complement is also regular. So L2 complement and L1 both are regular. So hence their intersection is also regular, which is the part B that we showed. So just to recap what we did, you are asked to find whether this A parity B language is regular, and we know that A parity B is nothing but L1 minus L2, where L1 is union A union B and L2 is A intersection B. That is something we observed from the set notation. So we know that union is regular and intersection is regular, hence L1 and L2 are regular. So only thing we wanted to show was that if you do set L1 minus L2, then that would also be regular. So again, using the properties of sets, what we got was L1 minus L2 is nothing but L1 intersection L2 complement. Then we use the properties of closure under complementation. So we know if L1 L2 is regular, then L2 complement is also regular. So now you are basically just doing intersection of two regular languages, so you would end up getting a regular languages. Hence what this means is A parity B is regular. So this is true for this proof. Does nowhere use the fact that A is a certain language and B is a certain language. When the argument that we did here was a very general one, we simply use the set properties, and using the properties of closure under complementation, union, and intersection, we showed that it is also closed under parity. So so hence in general, if you have any two regular languages, their parity would also be regular. So what you conclude is regular languages are closed under the parity operation. Yeah, so if there are any questions, please don't hesitate to ask. And the D part that was there in the question is basically A set minus B. So D part is basically asking you if A set minus B is regular. This is nothing but A minus B. Same thing but different notations. And here itself we saw that L1 minus L2 is already of this form A minus B, and we already saw using this argument that this is regular, so hence this is also regular. So yeah, so I hope that is clear. So all the four languages that all the four operations that we saw, union, intersection, parity and set minus. All of them are operations under which the regular languages are closed. So, yeah, if there are any questions, please feel free to ask. Otherwise, we will move to the next question. Okay, so I think there are no doubts. So I'll move on to the next question. So let me read out the question for you. You have been given two statements. The statement one is that if L1 union L2 is regular, then both L1 and L2 must be regular. And statement 2 says that the class of regular languages is closed under infinite union. So what do we mean by infinite union? Infinite union is basically union of infinitely many languages. So if you just have two sets, let's say A and B, and I say A union B, then this is a finite union. But if you say that there are A1, A2, A3, and so on up to infinitely many sets, and then I do a union of all of them, union of AIs, I in N, then this is an infinite union. So it's basically union but of infinitely many sets. Okay, so what you are asked to, what the question asks you to do is to tell which of the following statements are correct. So I'll wait for a minute or two, and you can please let me know your answers in the chat. Also, if there are any doubts about the question itself, please feel free to ask. Okay, so let's discuss. Okay, so the answer is both statements 1 and 2 are correct. Okay, sorry. Let's check. Okay, what this says is, let's look at statement 1. Statement 1 says that if L1 union L2 is regular, then both L1 and L2 must be regular. So note that the closure property basically says that if L1 and L2 are regular, then L1 union L2 is regular. But it does not say the other way around. So it doesn't imply that L1 union L2 is regular, then L1 and L2 must be regular. So that's not something that directly follows from the closure properties. In fact, what we will show is we will show a counter example for this. So let's say that L is some non-regular language. So at the moment, even if you don't know how to show a language is non-regular, just take it for granted that there are some languages that are sitting outside. So what I mean is, you have here set of all languages. These are all the subsets of sigma star, and we saw what are regular languages. These are languages that can be accepted by DFS. So there are languages, as you will see later in the course, that are outside. So there is something that a DFA cannot recognize. So at the moment, I'm not telling you what languages are there, but it's sufficient for the sake of argument to just assume that there are languages. So let me say that A is some language which is not regular. So A be a non-regular language. Just a minute. Okay. Okay, I hope it makes sense to say that there is some non-regular language, even if I'm not telling you what the non-regular language is, but you will see later on in the course. So let A be a non-regular language, or let me say L1. Okay. Now what I'm going to do is I'm going to define L2 to be the complement of L1. So everything that is not in L1 is in L2. So what can you say about L2? Is L2 regular? No. So why L2 cannot be regular? Because if L2 were regular, if L2 were regular, then we just saw that regular languages are closed under complementation. So that would mean that L2 complement, which is equal to L1 complements complement, which is nothing but L1, is regular. But this is a contradiction because we started with the assumption that L1 is a non-regular language. So this gives you a contradiction. Hence, it cannot be that L2 is regular. Therefore, L2 is also not regular. So now what I'm going to do is I'm going to take union of L1 and L2. What does that give? L1 union, L1 complement union. So basically this is everything that is there, because L1 complement has everything that L1 does not have. So hence this is equal to sigma star. And what do we know about sigma star? We know that it is a regular language because you can simply have a DFA like this that accepts everything, every string. So there is a one state simple DFA that accepts everything. So here what we have done is we have given a counter example which says that look, there is a language L1 which is not regular, there is a language L2 which is not regular, but if you take their union, then you get a regular language. So what does that mean? That means that your statement 1 is indeed false. That if L1 union L2 is regular, it doesn't imply that both L1 and L2 have to be regular. So we give a counter example. So hence statement 1 is false. This is false. Now let's look at statement 2. So statement 2 says that the class of regular languages is closed under infinity. So maybe I'll take a new page. So let us analyze carefully what is statement 2 correct. Okay, so again what I'll do is okay, yeah, again I'll show a counter example for this. So okay, so what we did was we showed that regular languages are closed under intersection, sorry, union and intersection. So if I give you a bunch of regular languages, if you take union of them, if A1, A2 and so on up to AN are regular, then by this property of closure under union, this implies that A1 union A2 union AN, this is regular by closure property. But the question says that is it closed under infinite union? So this is not something that the property guarantees. The property only works for finitely many unions. So what we're going to do is we'll show a counter example. We'll show that it is not true that infinite regular languages are closed under infinite union. So again, like we said earlier, we know that there is a non-regular language. So I'm not telling you what L1 is, but we don't even need it for the sake of argument. Just believe me that there is some non-regular language, and let's pick L1. So what can you say about L1? Can L1 be finite? So maybe like think about it for a minute. Can L1 be finite? Again, no. L1 cannot be finite, because if L1 were indeed finite, then what can I do? I can always design a DFA for it. So let's say that L1 is finite. So there is some there is some set of strings that is accepted. And uh, let's say that L1 is the length of x1, L2 is the length of x2, and LM is the length of LM is the length of xm. Then there is some number n by which I can bound the length of this. So let's say this set was AAAB, and so on, maybe like BBB. Then what is L1? L1 here is 2, 3, 4, 3. So since the set is finite, I can always bound the length of the string by some finite number. So in this case, it is 4. So so what my DFA can do is my DFA can go through all possible length 4 combinations over states and accept whichever whenever say it has read A, then if you reach this state, then you accept and so on. So since the set is finite, I can always bound the length of the maximum length of string which is accepted by some number, and I can always design a DFA for it. So yeah. So if L1 were finite, I could have designed a DFA, then it would have been regular. But since L1 is regular, sorry, L1 is finite, implies L1 is regular. So if L1 is non-regular, then L1 cannot be finite. So if you take contraposition of the statement, L1 is not regular or non-regular, implies L1 is infinite. Okay, so now what we can do is, let's say L1 is some set of strings x1, x2, and so on, but these are infinite. So what I will do is I will take each of the strings and I will design DFS for the same. So let's say M1 is the machine that accepts only x1. M2 is the DFA that accepts only x2, and M3 accepts only x3, and so on. So there are infinitely many machines like this. And notice that it's always, if I give you a string, you can always come up with a DFA for it. You just read that string whenever it stops, you accept it, and for everything else you go to the dead state. So all M1, M2, M3, and so on, these are all DFAs. So all MIs are DFAs. Okay, so if I take union of languages of M1, M2, and so on, union of language of MIs, then what do I get? I basically get L1, because L1 is x1 union x2 union x3 and so on. So on one hand, we have that all the MIs are regular, but L1 is not regular. So it is possible that you have infinitely many regular languages, but if you take infinite union of them, then the resultant language may not be regular. So yeah. So maybe like I'll let you stare at the proof for some time, and if there are any questions, please feel free to ask. Okay, so let me write here what we concluded is statement 2 is false. Okay, so the answer to this is D. Neither statement 1 and 2 is false. And how did we show that? We showed a counter example for both of them. For statement 1, we came up with L1 and L2 where the statement became false. And for statement 2, we constructed a language for which the statement does not hold. So this was slightly, I mean, a question involving some creative thinking. So I hope you appreciate. Okay, so if there are no questions, let's move on to the next one. So again, you have been given a set of statements, and you want to tell which of these are true. So let me read them out. So statement one says that, so we are talking about regular languages, by the way. So statement one says that every language is a subset of a regular language. Statement B says that if A is a regular language and B is a subset of A, then B necessarily has to be regular. Statement C is that union of two non-regular languages can be regular. And statement D says that if A is a regular language, then AC is basically the complement of A, then A complement is necessarily regular. So I'll wait for a couple of minutes. Okay, so this is basically A complement. So I'll wait for a couple of minutes, and you can let me know what you think, which of these do you think are true. Okay, so let's discuss. Okay, so let's look at each of the statements one by one. Let's look at A. So A says that every language is a subset of a regular language. My claim is that this is true. Why is that? Because every language is necessarily a subset of sigma star. That's something we know. And what do we know about sigma star? Sigma star is regular because, like we said earlier, you can always have a DFA for sigma star. So hence, every language is a subset of sigma star, which is a regular language. So A is true. Let's look at B. What does B say? B says that A is a regular language and B is a subset of A. Then should it be regular? So okay, so let's look at so this is false. Why is that? Because let me take A to be sigma star. Okay, and let me take P to be some non-regular language. So we know that this is, if this is sigma star, then these are regular language, and there is some language sitting outside which is not regular. But it is necessarily a subset. It is necessarily a subset of sigma star. So what do we know? B is a subset of sigma star, but B is a non-regular language. So this is not true that if A is a regular language, then every subset of it has to be regular necessarily. So how did we show that? We showed it with a counter example. Let's look at C. C says that union of two non-regular languages can be regular. So yeah, so we saw this previously. I mean, the first question or something, or I guess just the previous question, we saw that L1 was some non-regular language, and L2 was L1's complement, which we know by properties of complementation that L1 complement cannot be regular. Then, if you take a union of this L1 union L2, this is sigma star, which is regular. So again, like we saw earlier, you can have two non-regular languages, but if non-regular languages, but if you take a union of them, then you end up getting a regular language. So statement C is also for okay, sorry. Statement 2 is C is true. And what does statement D say? D says that if A is regular, then A complement is regular. So this is true by properties of closure under complementation. This is a closure property. And we saw a simple proof of this, and in today's tutorial also we saw a simple sketch of this by simply swapping the accept and reject states. So yeah, so what is the answer? Only B is false and all the other A, C and D are true. Okay. So yeah, if at any point if there are any questions, do ask. Okay, so let's look at the fifth question. So you have been given languages A and B, and these are not necessarily regular. A and B are some languages, and yeah, C and A and C is basically defined to be concatenation of A and B. So what do we mean by that? Um, if A is okay, so C is basically set of all xy such that x is in A and y is in B. So you take a string, some string of A, some string of B, and concatenate the string of A followed by string of B, and the resultant language that you get is what is C. So you're asked which of the following is true. Statement A says that if A and B are regular, then C has to be regular. Statement B says that if A is regular and B is not regular, then C is not regular. Statement C says that if A and C are regular, then B is regular. And D says that if C is not regular, then at least one of A and B is not regular. So I think I'll wait for a minute, and if you have answers, please let me know. Okay, so let's discuss. Um, okay, so let's again do the same thing. Let's look at each of the statements and analyze whether it's true or not. So let's look at A. A says that if A and B are regular, then C is regular. So this is true because this is a closure property of concatenation that we saw previously using epsilon NFs, that if you simply add epsilon transition from final states of A to to the start state of B, then you can construct an automaton for A concatenation B. So this is true because of closure under concatenation. Let's look at B. So what does B say? B says that if A is regular and B is not, then C is not. So for this, okay, I think there may be different ways of doing it, but one way would be that you take B to be a unary non-regular language. What do I mean by that? So, for example, this is, let's say, set of all U, set of all W, such that W is length of W is a prime. So, what does that look like? So, um, so one is a prime. Let's say, I mean, okay, let's start with maybe two. So two is a prime number. So 0, 0 would be in the string. Your sigma is 0. Or let me take 1. So this becomes 1, 1. So for this alphabet 1, all the strings whose length is a prime number is what we're going to write. So 3 is a prime number, hence 1, 1, 1 would appear, but 4 ones would not appear because 4 is not a prime number. Then you have 5 ones, then you have 7 ones, and so on. So basically, B is the set of all strings over 1 whose length is prime. So we will not prove this right now. Maybe at a later point we will prove that B is non-regular. So my claim is that if you take A to B, A to B sigma star, which is basically 1, 1, 1, 1, 1, 1, and so on. It's basically all the strings over, uh, including epsilon. So it's basically all the strings over 1 that are there in A. So what we're saying is B is some non-regular language, and I'm giving you A which is regular. Let's look at the concatenation. What does the concatenation look like? It will look like um, 1 1 followed by 1 1 1 followed by 1 1. Basically, earlier in B you did not have this string which is 4 ones, because 4 is not a prime number. But now if you concatenate it, you can get such a string. Why is that? Because 1 1 1 1 is a string which is in A. 1 1 is also a string which is in B. So if you concatenate it, you would get 1 1 1 1 in A concatenation B. Hence 1 1 1 1 would appear. Similarly, you can show that every string appears here. So you can have 5 ones and so on. So C is nothing but 1 1 followed by 1 star, which is the regular language, because you can also write a regular expression and you can also construct a DFA for it. So what we have shown here is that there are languages like this where one of them is non-regular, one of them is regular, but if you take a concatenation, you end up getting a regular language. So it does not matter in this case what is the order of A and B. Even if this were B concatenated with A, you would have gotten the same state, because same set, because the language is unary. So the order does not matter. So yeah, what we showed just now is that the statement B is not true. You can have a regular language and a non-regular language whose concatenation is not regular. So B is false. So okay, I'll maybe let you stare at the proof for a minute. Okay, let's look at the statement C. It says if A and C are regular, then B is regular. So, I mean, you can come up with different counter examples, or I mean, different yeah, I mean, different examples and so on. But what we did in B just now is itself a counter example, because what we showed here is that there is a there is an A, there is a C such that both of them are regular, but B is not regular. So this is exactly what we contradicted using this example. So by the same example, it follows that B and C are both false. And let's look at D. D says that if C is not regular, then at least one of A and B is not regular. This is true because it follows from the closure property. But let me write it again. So what does closure property say? That if A and B are regular, then C, which is concatenation of A and B, has to be regular. Okay. And what is the contraposition of this? This says that if C is not regular, then this is by closure property. And what does it say? That either, I mean, at least one of AB is not regular. So that is exactly what the statement D is. So D is also true. So the answer for this is only A and D are true. Okay. If there are any questions, please do ask. This is a good time to ask. Okay, so now we will look at slightly more advanced questions that will involve somewhat critical thinking. Okay, so let's define an operation which is called perfect shuffle. So earlier we saw these operations like union and so on. This is somewhat of a complex operation. So what is a perfect shuffle? Perfect shuffle basically, uh, let's say let's say A is a regular language, and maybe it looks like birds, cat, dog, let's say, and B is another language which looks like pot, time. Okay, so what does this perfect shuffle do? So perfect shuffle basically takes let's say some um, okay, so in this case maybe the sigma is BIR. Okay, maybe I'll not write everything, but let me just show you an example. So perfect shuffle takes one letter from here. Um, yeah, takes one letter from here, then takes maybe one letter from here, takes another from here, then another from here, then one from here and one from here. And it goes on doing like this. So if you do the perfect shuffle operation over cat and time, then what do you get? You get C, T, A, I, T. Okay. In this case, it's not possible to do it because the lengths are not same. But maybe I'll show with word and time. So if you do B, T, so you can get things like this. So what we did here, what does it do? It takes one string from A, let's say cat, and then one string from B, let's say pot. What does it do? It takes first letter from A, second letter, then first letter from B, then second letter from A, second letter from B, then first letter from A, and a third letter from A, and third letter from B. So it's basically that you have cat, but in the blanks here, you're going to fill it with the letters of letters of B. So you're going to write pot over here. So it does this operation. So it's kind of shuffling two words in a very specific way. So the name comes from the idea that if you have, let's say, two deck of cards, one of diamonds and the other of spades, and if you shuffle them such that there is this alternating sequence of hearts and diamonds, spades, diamond, spade, diamond, spade, and so on, then you have made a perfect shuffle. So it takes the idea takes inspiration from your cards. So yeah, so I hope the operation makes sense now. So this is the operation that we're doing, and what it asks you is, if you do this operation, then the resultant language that you get, let's call it perfect shuffle of A comma B, is this language regular? That's the question. So I'll let you think about it, and you can let me know your ideas or yeah, any doubts you have. Okay, so let's discuss. I hope you had enough time to try this out. Um, okay, so my claim is that this is a regular language. Okay, so how do we show that? Generally, if you have to show that something is regular, you either come up with a regular expression, or you come up with a DFA, or you come up with NFA, or like any of the equivalent models. Any one of them is sufficient to show that it is regular. So that's what we're precisely going to do. We will try to draw an automaton for this language. Okay, so the idea is that we'll do something very similar to what we did in the case of product construction. So what we will do is we will modify the product construction. Okay, so how does this work? Every state here, we will redefine our states. So every state here will consist of two tuples, p comma q. So what does this mean? So it tells you that, maybe let's call, okay, p comma q. So what does this mean? P tells you the state that you had read previously, and q tells you the sigma, um the element that you read previously. So why do we need that? Because you're sort of like, you're sort of simulating the machine for cat, but only thing is, at every point something else is coming up. You're sort of in the middle, you want to simulate B. So what you do is you simulate one step of A, then you do one step of B, then you do the second step of A, then the second step of B, and so on. So it's just that you want to remember what what is the string you read previously, and so on. So okay, sorry, q, maybe I'll call this, if q1 is the set of states of the first machine corresponding to A, maybe I'll call it qa, and q is the corresponding to qb. So if you were at some state of A, and let's say you read a, maybe I'll do a simulation for this language. Then let's say if you see a C, then it takes you to P, maybe let's say takes you to some R on seeing a C in the machine corresponding to A. So where will I go? Hi. Okay, so just that, I mean, now that you've joined, I'll quickly recap what the question that we are attempting. So yeah, so this perfect shuffle is an operation that sort of shuffles two strings from different languages in the following peculiar way. So let's say that bird, cat, dog, these are, let's say, strings in A, and let's say the strings in B are pot, time. Let's see how this shuffles. So you take one string from here, let's say cat, and you take the other pot. How does this shuffle? You write cat, but in the intermediate spaces, you're going to write pot. So basically, you take first letter of the first string, first letter of second string, then you take second letter of first string, second letter of second string, and so on. So it's sort of shuffling the two strings in this way, and you're going to show that this is a regular language. So how do we show that? We will do the product construction like earlier. So yeah, so just to connect you with the question. Okay. So let's say in the first automaton, if you were at state P and you see a letter C, then you go to R. So what we will do now, we will go to R. Okay, R followed by, let's say, MB. Let's say that S is the start state of the second machine. So since you've not seen anything of B, you will go to S. So what this tells you is now you have read C of the first string, and you're going to read P. So at P you want to simulate the machine B. So let's say yeah. So let's say you are at S, and on reading P, it takes you to some state S1. So what you will do is you will go to S1, but you will remember your state in the previous machine. So you write R comma S1. Now you look at the machine M1. If on R, on seeing okay, I'll draw it on a fresh page. Let's say that machine A did something like this. You were at state S1. On seeing C, it went to S2. On seeing A, it went to S3. On seeing T, it went to S4. And there are other transitions that I'm not drawing because I'm just showing you one part of the simulation. And MB does something like this. It starts at P1. On seeing P, it goes to P2. On seeing O, it goes to P3. On seeing T, it goes to P4. And since pot is indeed a letter in the language B, P4 would be final, and there would be like other transitions out here. I'm not drawing that. So what I'm going to show is how does the perfect shuffle for AB look like on the string C8T shuffled with POT. So what we're going to do is you start with S1 comma P1 because S1 is the start state of MA and P1 is the start state of MB. This is your start state. Now you read C. So where does the first machine take you on C? It takes you to S2. So on C you go to S2 comma P1. The second state you're going to retain. Now you want to simulate P but on the second machine. So on second machine, if you are at P1, it takes you to P2. So on seeing a P, you go to S2 comma P2. Now you want to read A on the first machine. So S2 takes you to S3. So you will go to S3 comma P2. Now you want to simulate O but on the second machine. So P3 takes you to P2 takes you to P3. So on O you retain S3. From P2 you go to P3. Then you want to read T but on the first machine. S3 takes you to S4. So S3 takes you to S4 and P3 on T, and you want to read a T on this machine, and P3 takes you to P4. So yeah, so that's basically this is basically just the same as product constructions. Every time we have the states that we have are sort of Cartesian products of the sets in the first machine and the sets in the second machine. Then you have all these states. Only thing we did was we modified the transitions. So in odd number of transitions, you are simulating first machine. In even transitions, you are simulating second machine. So what I mean by that is, if you are in the first transition, you look at the first part, S1. S1 takes you to S2, so you make a corresponding transition and retain the second part. Then you have an even transition. In even transition, you simulate one step of M. So that is P1 takes you to P2. So that's what we did. In the third transition, you simulated next step of MA, which is this. S2 takes you to S3. Then you simulated the second step of this, then this followed by this. So that's the order. If I tell you like this one followed by this one, then this followed by this, and this followed by this. So that's exactly what we did. So it's just a modification of perfect shuffle. That so as just to demonstrate a different example. Okay, so if there are any questions, please ask. Otherwise, we'll move on to the next question. Okay, I hope that was clear. So let's move on to the next question. So here is a different language which is called shuffle. So what does shuffle do? It's similar to what you did earlier, but you are not sort of taking one string and uh, sort of merging it with the other string. You're kind of joining different strings together. So just so if this were pot, cat, tap, and B were, let's say, kettle, leaf, and something like this, then shuffle would do the following. Shuffle takes one string from A, let's say it takes pot, then it takes one string from B, let's say it takes leaf, then it takes one string from A again, then it takes one string from B, and it sort of keeps on doing one string of A followed by the other string of B. In earlier, what we were doing is we were taking um, two strings here and interspersing the letters. So it was like P L O, like pot, which was interspersed with, let's say, L E A F or something. Now we are instead taking two strings, different strings, and alternating them, one string from A followed by one string from B followed by one string from A, and so on, alternating in this fashion. So this is what is the shuffle operation. So what you are asked to show is if A and B are regular, then shuffle of A comma B is also a regular language. So by the way, just to clarify, this is one string of shuffle. There could be lot of such strings. So I'll let you think about this for a minute, and if you have ideas, we can discuss. Otherwise, we'll look into the solution. Okay, So let's discuss the solution. Okay, so let's say that since A and B are regular, there are some machines, some DFAs corresponding to it. So let's say that this is some machine, um, some machine corresponding to the language A. Then there is some machine corresponding to B. So let's say that is NB. So you have like the start state, maybe a bunch of transitions like this, and there could be some final states along the way. That's what they look like. What we're going to do is we're going to modify some of the operations, some of the transitions, so that the resultant machine now recognizes the shuffle language. So what we want is we want to read first some string in A. So when have we read some string in A properly, that would be when you have reached one of the final state. So for example, if cat is a string in A, then on reading cat you would have reached final state. So precisely those strings, those strings that end up in final state are the ones that are in A. Now what we want to do is after seeing a string in A, we want to start seeing a string in B. So what does that intuitively, what that means is if I am at a final state here, I immediately want to jump to a start state of B. So from all the final states of A, we will draw epsilon transitions to, so from Q on epsilon goes to P1, where Q is a final state in the machine N. Okay, so that is the first modification we did. Okay, second thing is, if let's say now you read some string in B, maybe let's say leaf. So if you read leaf, it goes something like this and it would reach a final state. Now, if you reach a final state, do we want to stop there? No, because look at the language carefully. It reads one string of A, then it reads one string of B, then it reads one string of A, and so on. It keeps on doing this. So it is possible that even if you reach here, some final state of B, you may still want to read something. So what do? You basically add epsilon transition to the start state of A. So what do? Delta P epsilon is equal to, this is P1, which is the start state of MB. You go to high, you go to S1, which is for all the states of B. So what we have done here is, you start at S1. If you end up reading a string in the language, then you immediately jump to the next machine. Then you read some string in B. Then you immediately jump back. So what this is doing is, it is reading a string in A, followed by string in B, followed by string in A, and it keeps on doing. Now there is one small modification we need to make. Why is that? Because when we said this, when we defined this, you started at A, you then B1, A2, B2, you ended at BK. So you don't want to, for example, you don't want to accept cat because it only ends in a string in A. You want to accept if it is something like cat followed by leaf because this is in B. So that means you don't want to end, for example, if you read cat here, you don't want to end here. That means you simply make them non-final states. So the third modification that you will do is, your state of final states is only those B which are final states in the automaton B. So with these set of changes, you are done. Also, like if I modify the language slightly, if I allow you to end in BK or I allow you to end in AK, either of these, then you don't need to make this third modification because it's okay if you read a cat and you end there. So let me quickly recap what we did. So you have this language shuffle which concatenates like a string of A followed by string of B followed by string of A and so on, where A and B are regular languages. So this is what it does. It sort of shuffles the strings in the language. So like if you have this is A and this is B, then cat followed by leaf is a string, is a valid string, or pot followed by leaf, pot from A followed by leaf from B followed by cat from A followed by kettle from B, and so on. All sorts of shufflings. What we wanted to show is that this is regular. So since A and B are regular, here is some machine corresponding to language A, and here is some machine corresponding to language B. Okay, and S1 is the start state of first machine and P1 is the start state of second machine. What we wanted to do was we simply did three small modification. First, we said that if you read some string and end up in a final state, then by our requirement, after reading a string in A, you want to read a string in B. So you simply made an epsilon transition to the start state. So from all the final states over here, you collected all of them, added an epsilon transition to the start state of second machine. Now you read a string in B. Now you don't want to stop here because it goes multiple alternations. So it can say cat followed by kettle followed by pot followed by leaf, and it can go on. So after reaching a final state here, again you don't want to stop. You want to start back again. So you added epsilon transitions from final states of B to the start state of A. So that is the second modification that we did. Okay. And the third thing was, because we don't want to stop at a string in A. So if you read at A, then B, you can accept. But if you read a string in A, then a string in B, then a string in A, you don't want to accept because that is the condition that is given to you. You want to end in a string in B. So we did a very simple modification. We simply took all the final states here and made them non-final. That's it. So yeah, if there are any questions about this, please do ask. I'll maybe show you this for a minute. Okay, so I'll move on to the next question. Okay, maybe let's take this one. Sorry. I'll go back to the previous question, but for now, let's take this one. So L is a set of all strings W such that there are equal number of 0, 1 and there are equal number of 1, 0. So what does L look like? L is something like 0, 1, 0 because there is exactly one occurrence of 0, 1 and there is exactly one occurrence of 1, 0. And then you can accept 1, 0, 1, 1, 0 or 0, 0, 0, 1, 1, 1, 1, 0 and so on, or say like 0, 1, 0, 1, 1, 0, 1, 0 and so on, like right. I mean basically the number of occurrences of 0, 1 in W should be equal to the number of occurrences of 1, 0 in W. That's it. So yeah, so that is the language that you have and you want to show that it is regular. So maybe you can think about it for a minute and we will discuss. Okay, so let's discuss the answer. So what you can do is you can try to come up with a DFA, you can try to come up with an NFA or something. So let's see how to design a DFA for this. So if you are at a start state here, maybe I'll call it 1. Okay, and then you see 0. Let's say you go to 2. Then if you see a 1, then you have seen one occurrence of 0 1 at this point. Now if you see a bunch of ones, you haven't seen any more 1 zeros, or you haven't seen any more 0 ones. At this point you have only seen one occurrence of 1 0. But now if you have seen like bunch of ones, um yeah, now if you see a 0, then you have essentially seen one occurrence of 0 1, and you have seen one occurrence of 1 0. So if you are sort of keeping a count of how many 0 1s and how many 1 zeros you have seen, this is sort of nullifying it. So one occurrence of 0 1 nullifies or cancels off with one occurrence of 1 0. So if you, at this point, if you see a 0, then you should accept it, because you have seen same number of 0 ones and same number of 1 zeros. Okay, but let's say you had taken a different route. Let's say you saw a 1 first. Okay, so sorry, this is not, sorry, yeah. Then let's say you have seen a 1, and if you see a 0, yeah, then you have seen one occurrence of 1 0 at this point. Okay, so now if you keep on seeing multiple zeros, then you have still seen exactly one number of 1 0. At 6, you have only seen one occurrence of 1 0. Now, but if you see a bunch of zeros, let's say, now if you see a 1, then you have seen exactly one occurrence of 1 0 and one occurrence of 0 1. So you are sort of nullifying the count. So you go to, let's say, some final state on 1. Let's say 7. Now, if you are at 7 and you see a bunch of ones, you stay there. But if you see a 0, so let's say you saw a bunch of ones. Now, if you see a 0, you have seen exactly one occurrence of 1 0. And who keeps track of that? This guy does. So 6 is the state that keeps track of 1 0 that was seen. So this is, if you see 1 and if you see a 0, then you reach a 6. So 6 is the state that sort of keeps track of exactly one occurrence of 1 0. So even if you have like sort of seen 1 0, then you saw 1. So at this point you have seen equal occurrences. Then maybe let's say you see a bunch of ones, that doesn't add to anything. But if you see a 0 now, then it's as good as you have seen one occurrence of 1 0. So hence you go back here. Similarly, if you are at 4, if you keep on seeing zeros, it's not adding anything further. But now if you see a 1, then you have seen one occurrence of 0 1, which is what this this state captures. If you see one occurrence of 0 1, 3 is the state where you should go. So yeah, so that's basically the DFA corresponding to it. And since you can draw a DFA for the language is indeed regular. Okay, so but there are other ways of doing it. You can draw an NFA or something, but you can also directly write a regular expression without even drawing the automaton. If you can just simply come up with a regular expression for it, then essentially the language is regular. So let's do that. Okay, so yeah, so how do you do that? Let's say you see a bunch of zeros, then you see a 0 1, then maybe you see a bunch of ones, and at a later point you see a 0. Then this part takes care of the fact that you saw 0 1, then you saw something else, then you saw a 1 0. So you saw equal number of zeros and ones, and there could be zeros following that. Or it could so happen that you see a 1 0 first, then you see a 1 0 after reading a bunch of zeros. So it could be that you see 1 0 followed by maybe, or there may be some zeros, there may not be. Then ultimately you see a 1. And maybe later on also you see a bunch of ones. But this string here is only capturing, you saw one occurrence of 0 1 and one occurrence of 1 0. This string is only capturing that you saw one occurrence of 1 0 followed by one occurrence of 0 1. But this could happen multiple times. For example, you can have 0 1 0 1, 1 0 1 0. You can have strings like that. So what you will do is you will simply do a clean closure of this. So for example, if you want to get this, how do you get, how can we obtain? Let's say first you take this one. So you have 0 1 0 1 0. That's it. So you've gotten this part. Now let's say you take this part, and from here 1 star 1 0 0 star 1 1 star, I can obtain 1 1 0. Yeah, 0 1. And notice that there are a few trivial strings that we haven't added yet. So for example, L definitely contains 0 star, and it definitely contains 1 star, because it has 0 occurrences of both strings 0 1 and 1 0. So you should basically add 0 star and 1 star to this set. So in order to obtain uh, the last 0, you can borrow it from here. So simply take this from 0 star. So if I call this R1, I call this R2, then you obtain 0 1 0 from R1, you obtain 1 1 0 1 from R2, and 0 is something you obtain from 0 star. So yeah, so you can directly write the regular expression sometimes. It may be very exhaustive to draw DFAs or something. Then it's possible that regular expression is easy way to show that a language is regular. And since we showed that all of these models are essentially equivalent, it's enough to show one of the one of it. I mean, one of the models. Okay. Yeah, and this is not a unique expression. There could be multiple expressions corresponding to the same language. So if you might have tried, you may have gotten something else as well. Okay, so if there are any questions, please ask. Okay, so I'll show the next question. So let's say L is a regular language, and we know that L reversal is the set of all strings written reversely. So if L is, let's say, apple, um, apple, custard, something, then L reversal basically reads each of the strings in reverse order. So this would be E L P P A D R A T S U C and so on. It's basically reading every string in the reverse order. So this is your L reversal. And we know that regular languages are closed under reversal. We saw this in one of the tutorials as well. So if L is regular, then L reversal is also regular. So what the question is asking you to show is, you're not asked to show that this is regular, but instead we are asking, since every regular language has an expression corresponding to it, so if let's say R is the expression corresponding to L, what can you say about the regular expression of this language LR? So I'll give you a couple of minutes to think about it, and if you have any ideas, please unmute and share, or you can write in the chat, and we can discuss. Okay, so let's discuss. I hope you had plenty of, I mean, I hope you had enough time to think about it. Um, okay, so, right. So, what we do is, I mean, the idea is very simple. If you, I mean, um, if I tell you that, let's say, um 0, 1 star is some regular expression, or let's say 1, 0, okay, let's do it this way. So 1, 0, a plus b, 0 plus 1 star. This is some regular expression, let's say. So what is the language corresponding to this? This is set of all strings. W starts with 0, 1. So what is the reversal of this language? The reversal of this language is set of all W such that W ends with, sorry, this is 1, 0. I hope there is no confusion. Okay, so R is a regular expression of the form 1, 0 followed by 0, 1 star. What we did is we simply wrote the language that it is recognizing. It's recognizing everything that starts with 1, 0. Now, what is the reversal of this language? The reversal would be every string that ends with a 0, 1. Because if you read, let's say 1, 0, 0 in the reverse order, that is 0, 0, 1. So it's everything that ends in 0, 1. So what my claim is, I will write a regular expression as follows. I'll simply reverse my regular expression. What do I mean by that? So I take this, the last part of the regular expression, I write it first. Then I read the second regular part of regular expression from the end, which is 0. Then I read the last one and write 1. So my claim is that if you have a regular expression, you simply write it in the reverse order and you would get a regular expression for the language LR. So in this case, you can also match it. What is the language, if I give you this regular expression, what is the language of R prime? R prime is everything that ends with 0, 1. This is exactly what we wanted, which is LR. So um, yeah, so even if you have like complicated expressions, b plus a plus followed by a b and so on, the reversal is basically you break it into small chunks and reverse each of them. So if you read this in reverse order, you have a plus b plus followed by a star followed by b and so on. So I hope it is clear what we mean by reversing the regular expression. And you can also like formally prove this by induction that this is indeed correct. That if you simply reverse the regular expression, you get the um, regular expression corresponding to the reversal of the language. So yeah, so that is one question. And yeah, if there are any doubts at any point, please do ask. So at the beginning, we said that we know how to go uh, from a regular expression to an epsilon NFA, and from epsilon NFA, you know ways of going to DFAs, NFAs, and so on. But we are not seeing the other direction in the previous lecture. That is, we did not see if I give you a DFA, how to get a regular expression. So that is something we will do. So I'll go to the question. Okay, so what we have done is here is a DFA, and you want to write a regular expression corresponding to it. So I'll wait for some time, and if you have some thoughts, you can share, and we will discuss the answer. Okay, so let's discuss. So like, I mean, like everything that we have been doing so far for getting from NFA to DFA or anyway from any of the machines to any other machine, we saw a step-by-step procedure for doing it, and that's what we're going to do here as well. We're going to show like you can do trial and error, or you can make observations and check if like come up with a regular expression. That is always possible, but but if you have like really large DFAs with say hundreds of states, then the task is challenging. So yeah, so it's always good to have a procedure. So that's what we're going to discuss. So we may not be able to compute everything in this tutorial right now because it's almost 8, but I will still discuss the general idea and we will start, uh, we'll do it. So, so the idea is very, I mean, the intuition is as follows. So if I want a regular expression from, let's say, some state P to some state Q, which is a final state, let's say, and this is, let's say, your start state. If I want to find a regular expression of this automaton, there are states in between and so on. Then, um, um, then how can I get it? It's possible that maybe, okay, let's say for the ease, let's say these are labeled. Let's say these are labeled 1, 2, and so on, and this is some n. So if we want to go to 1 from n, then all the states that I can read are 1, 2, and so on up to n minus 1. These are the labels. So yeah, so if I'm at state I and I want to go to state j, using hello. So yeah, sorry if you are saying something I could not hear you. Can you, if there's something you want to say, can you please write in the chat? Okay. Yeah, so this is the regular expression corresponding to with from start state I to state j, reading only the states from 1, 2, and so on up to k. Okay, so how do you go from 1 to 1 to j, maybe, or let's say I to j? It is possible that you okay, it's possible that the states that you ended up reading were 1, 2, and so on up to k minus 1. You never ever read k. So in that case, what is the regular expression? It is Rij k minus 1. Or it is possible that you indeed in some path you went to k by reading the states in between 1 to k minus 1 or any of it. And then from k to j, there may be a way to go to from k to j. So it's possible that you directly go from I to j without even reading a state k. That is what this captures. Or it is possible that from I to k, I mean, you go to k by some path, and from k to j you go by some other path. So let's write the expression corresponding to the second part. So uh, this is Rik, because from I you are going to k, but you are only reading labels from 1 to k minus 1. Then from k to k, there may be some loop or something that takes you back from k to k by reading k minus 1 states. And you can take the loop as many times as you want. So hence this star here. And then from k, you're going to j. So that is Rkj. Again reading k minus 1 labels only. So yeah, that is the expression. So from I, if you directly go to j without even reading k, then this is the expression Rij k minus 1. But if you do read a k, then then you go from I to k, that is what this captures. Then there may be a loop over here, that is what this captures. And then from k to j is the remaining part of the expression. So if I give you some automaton, what do I want to find? Let's look at this automaton. I want to find the regular expression from starting from 1, ending at state 3, So I'm reading Q1 as 1, Q2 as 2, and Q3 as 3. I hope that is okay. So I want to find regular expression from starting state from 1 to 3, and uh, what am I allowed to read? I'm allowed to read the states 1 and 2 in between. So yeah, so that is what I want to find out. What we will do is, um, we will break we will find small expressions for each of them, and simply keep on plugging and placing into the formula. So let me get this TFA over there. So okay, so this is the DFA that we have. Now we will start drawing the table. So I'll also maybe write the formula once. RIJK is either you go without reading K, or you go from I to K. And you go from K to J. So what we will do is we will make a table. So yeah, so let's say here we are writing R11, then you want R12, R13, R21, and here I am writing the values of K. Ultimately we want to find R132. So we will start with K equals 0, K equals 1, and K equals 2. So let's try to fill in the entries into this column. So what does R110 mean? R110 means I want to go from state 1, come back to state 1, but in between I'm not reading anything. So 0 basically means there is no state whose label is 0, so I'm not reading anything in between. What does that mean? That means, is there a direct transition from 1 to 1? So in this case, in this example, is there a direct transition from 1 to 1? No, because 1 goes to one goes to state Q2 on AB. So I will write epsilon here. Now you can check for R12. From Q1, can I go to Q2? I can. So what am I reading? What can I read? I'm allowed to read A plus B, because you have this transition from Q1 to Q2 on AB. Then let's do 1 3. From Q1 to Q3, is there a direct transition, direct arrow from 1 to 3? No. So this is epsilon. Let's do the rest of the thing similarly. From 2 to 1, there is an arrow on A. From 2 to 2, there is no self loop. From 2 to 3, I can go on reading a B. From 3 to 1, I can do A plus B. From 3 to 2, there is no transition, and from 3 to 3, there is no self loop. Okay, so let's try to fill the entries into the second column. So maybe I'll write over here. I'll get some space here. So what does R111 look like? This is R. I'm simply putting I equals 1, J equals 1, and K equals 1 in the formula here, in this formula. So what do I get? I get R110 union R110, R110 star, R110. This is what I get. Now notice that since we solved these values for K equals 0, you already have all these values into the table. All of them in this case are epsilon. So if you concatenate everything, you end up getting epsilon only. Let's do the same thing for 2. So let me change these things. Okay, so if you have R12, then I is 1, J is 2, and K is 1. So you have R12, R11, R11, R12. Now let's look up the values of R12 and R11. So what do you get? R12 is A plus B union R11 is epsilon and R12 is again A plus B. So this is what you get. If you sort of plug and place, maybe I'll do it. So R12 is A plus B. Then you have union over R11 is epsilon. And you have again R11 star, which is epsilon star. Then you have R12, which is A plus B. So this is nothing but A plus B. So that's why the entry over here is A plus B. Let's do one more time. Okay, let's do R13. So R13 according to this formula is R13 with 0, R11, R11 and R13. So let's do it again. R13 is epsilon, R11 is also epsilon, so you just get epsilon. So you can basically go on checking this, but let me show you that this is indeed correct, that whatever we're doing is consistent with the automaton we have. So let's maybe check this entry R12. So if I look at this automaton here, if you are at Q1, you want to go to Q2, but you are only allowed to read the states 1. You are not allowed to read 2 and 3 in between the transitions. Why am I saying that? Because K is 1. So K tells you what labels you can read. So I'm only allowed to read 1. Then what all things can I read? So let's say you are at Q1. I can go to Q2 by simply doing A plus B. So A plus B is a valid thing. Then I can okay, I think I can go back to A again, and yeah, and basically come back to Q2. So okay. Oh, okay. Sorry. So this is not allowed. Yeah. So okay, let me repeat it again. So if you are at Q1, you want to go to Q2, but on the path you are not allowed to read Q2 again. So this transition is there. So there is a transition from Q1 to Q2 on A plus B. So A plus B is something that you get. Now the other thing that I was saying is, let's say you read A or B, you go to Q2. There is one transition here from Q2 to Q1. So let's say you follow that. Sorry. Yeah. Let's say you follow that. You come back to Q1. Then that means you see an A. Now you want to ultimately you want to go to Q2. That was the plan. So if you have to go to Q2, you will have to read A or B. So that means on the path you basically read one. You read one, then you went to two, then you went to one, then you went to two again. So on the path in the middle you read a two. That is not allowed because K is 1 for us. So in this entire journey, before you finally hit 2, you start with 1, you end at 2, but in the middle you are not allowed to read 2. So if you were to take this loop like this, from Q1 to Q2, then Q2 to Q1 and Q1 to Q2, you have reached Q2, that is fine. But in the middle, you visited Q2 again. That is not what K equals 1 allows. That is something that would be valid in K equals 2. So K equals 2 will allow you to read states like 1, 2, 1, 2 and so on. Okay. So hence this is indeed a valid expression. So yeah, so you will not get something like this because you are not allowed to visit Q2 again. So A plus B is the only thing you can get from Q1 to Q2 if you are only allowed to read Q1 in the middle states. So yeah, so I'm not the rest of the process is like very mechanical. If you want to find R21, then you simply put I equals 2, J equals 1 and K equals 1 in this formula. and all the values are already calculated here and here. Simply using that, you're going to fill all the entries. Ultimately, the entry corresponding to R13 at 2. So this is the entry that would be our answer. This is R132, meaning from start state 1, you go to the final state 3, but on the way you only read Q1, Q2. So, yeah, so this is the Yeah, so this is the final thing you want. So if you go on filling the table, ultimate. Okay, I think I'm missing something. I think there should not be 2, but there should be 3, because from 1 to 3 you should be allowed to read 1 to 3 in order to capture the entire expression. Yeah. So sorry. I think you'll have to go like one more column over here. You have to go from up to k equals 3, and R133 would be the answer that you were looking for. So the only thing that I wanted to convey is that there's a very intuitive method, process to get a regular expression. What you did was, you started at a state, you want to go to some state, you want to capture the regular expression on the way. So you looked at all the possible paths using the label. In this case, it so happens that there is only one final state, which is Q3. So it is enough for us to find this value R133. But let's say the automaton looked something like this. You are at 1, then you go to 2 on something maybe. There is one final state here. There is 4, 5, 4, 5 or something. And I don't know, there's transitions like this. And let's say there are multiple final states, and there is something like 7. Now it is not enough to find R13 using all the labels up to 7, because that will only tell you those strings that end up at 3. It is possible that string is accepted because it reaches the state 6 or it reaches the state 7. In that case, what we will do is we will find separately what is the value of R167, what is the value of R177. That means this captures all strings that reach state 3. This captures those that reach the state 6, which is final state, and this captures the ones that reach 7. So what is the language you accept if it reaches 3 or 6 or 7? So what we should do is we should simply do a union of all the regular expressions. So if you have multiple such final states, then in this table you will look for the appropriate entries, and ultimately you will take a union of all of them. So I think, yeah, that is all I wanted to discuss today. There are some examples that we could not cover because we have already exceeded time. So I will try to take them in the coming session. And yeah, I think I hope the session was helpful. We will meet again next week. Next week on Friday, 6 to 8 p.m. Sorry. So, okay, thank you all. I'll end the call, or maybe I'll stop the recording. If there are any questions, I'll wait for 5 minutes.